The stress-strain diagram that we constructed gives us a fundamental description of material behavior. In this video, we'll talk about some of the different other material behavior descriptors, the elastic modulus, yield strength, and Poisson's ratio. The elastic modulus, typically denoted with just the letter E, describes this relationship, summarizes it. If we look at other potential stress-strain diagrams, which might look like this or that, this one, if we take a look at how this material behaves, it takes a lot of stress in order to get a little bit of strain. This material here takes a little bit of stress and we get a lot of strain. So we see this slope of this line describes how stiff the material is. The steeper the slope, the stiffer the material. Now the material that we described a moment ago had this stress-strain curve that looked like this. If we want to determine how steep this slope is, we'll take one of its data points and we'll divide its rise divided by its run. 50 psi divided by 0.1. Take our stress divided by our strain, and that equals 500 psi. That's our elastic modulus of this material. Now this is a very small elastic modulus for most materials. Things like steel has an elastic modulus much larger. So as you can see, the material we were playing with a moment ago, very soft compared to this very stiff steel. The yield strength also shows up on a stress-strain curve typically. Typically it's the point where the stress-strain curve goes from the linear region to the nonlinear region. Now there's several other points in here, and I encourage you to read more up on stress-strain diagrams, and they'll show you some graphics. It'll show you things like proportional limit, elastic limit, and so on. But we're going to describe this point where it transitions from linear to nonlinear as the yield stress. That's the point where the material starts to permanently deform. We'll denote this with sigma sub y. For many steels and aluminums, we talked about this in the unit section, but you'll see yield strengths somewhere in the ballpark of 200 or 20 to 200 KSI. Those are the kinds of pressures it takes to have those materials permanently deform. Finally, Poisson's ratio, another important property for the purpose of our analyses, describes this effect. If I put a compressive load on something, it tends to strain in the other directions. It'll expand outward. So not only does it shrink a bit, but it also stretches a bit. And the degree to which it stretches is described by this Poisson's ratio. The ratio, described by the letter nu, it varies between 0 to 0.5. If you look in the database, you'll see numbers between those two values. Things on this extreme, on the 0.5 extreme, implies that every unit that I compress it this way, it'll expand by half a unit in the other two directions, such that the volume, the initial volume, is equal to the final volume. So the volume doesn't change. We call this incompressible material. Things like rubber, when you push it in one way, it tries to stretch in the other directions. Highly incompressible. It has a Poisson's ratio very close to 0.5. Things on the other extreme, Poisson's ratio is close to 0. That implies that when I compress it this way, it expands by nothing in the other directions. So it just simply compresses. Things like foam, you can imagine taking a piece of foam and compressing it down to a small ball. You can change its volume perhaps very easily because it's got a lot of voids. Most materials we'll be using will be like steels and aluminums. They'll have Poisson's ratios between 0.25 and 0.3, so they're somewhere in the middle of the mix there.